Assalamu alaikum warahmatullah. This is Tripoli 4862, your VLSI design lab. So our today's experiment will be RTL synthesis, gate level implementation of a full adder using Cadence Genus. Previously, we have already talked about what RTL synthesis is, why is it necessary, what is its position in the AC design flow. We have talked about our Verilog RTL file.p file, our constraint r.sgc file, and we have also talked about our TCL script, our tool command script. So we have done all of that, and we have already seen the commands that we're gonna use while doing RTL synthesis, and we're gonna use a full adder as an example. So let's get started from here. That is preparing the RTL synthesis environment. So for that, you're gonna have to log into your Cadence account. I have already logged into mine. So we can get started. Let me split the screens. So the first task is creating the RTL synthesis directory. We're gonna have to create a dedicated folder with some subfolders. So we have already learned how to create folders using our mkdir make directory command, but we did it one by one. But here we can use a single command in order to create the entire directory to save time. So it should be something like this: mkdir give space then full adder lab 3. We're gonna create the folder full adder lab 3, and then we're gonna create three subfolders: RTL, constraint, libs, synthesis, and output. So if I just press enter, it should be created. So if I press the ls, it's gonna show me the full adder lab 3. Is there any full adder lab 3 here? Here it is. So I'm gonna enter the full adder lab 3 full mm, lab 3. So I'm inside the full adder lab 3 folder. If I press ls again, we're gonna see 5 subfolders for our RTL synthesis environment. Okay. So the next command was cd full adder lab 3. We've already done that. So we are inside our directory. This is the purpose of each directory. Our RTL will contain the Verilog code.v. A constraint will contain the SDC code. Libs will contain your slow.lib. Synthesis is the working directory where Genus is run and the TCL script lives. And finally, your output will contain your netlist and the generated reports. So there is a note. Genus TCL command typically uses relative paths. There will be a relative path within your TCL script, which is relative to your synthesis folder. So the synthesis folder is normally used as the working directory from which the Genus is launched. Your TCL script will remain in synthesis, and there we will launch our Genus. So let's start with creating the Verilog RTL file. We're gonna have to enter our RTL subfolder, RTL. So we're inside RTL. Earlier we used our gedit option. Now we're gonna use another command called nano in order to write a code. So we'll write nano full adder dot v. So if I just press enter, it will say this command. So gedit basically uses a graphical user interface, but using nano basically means using the terminal for writing your codes. We are not using any graphical user interface here. You're just using the normal Linux terminal as our writing environment. So we're gonna have to write the Verilog code for our full adder. This is the code. I have already copied the code here. There might be some formatting issues, so be sure to format it before pasting it. So full adder input A and B and C in output is sum and carry out. Your assigned sum is basically an XOR operation of A, B, and C in, and your carry out is the OR operation of the individual ANDs in module. So in order to save it, you're gonna have to press Control O, enter, and then exit with Control X. So press Control O. It will say file name to write fullada.p. Press enter, enter. Then in order to exit, you're gonna have to write Control X, Control X. Then you have exited after creating your fullada.p or RTL code for fullada. This is the line by line explanation. I'm not gonna get into those. You already know about all of this. Then we're gonna have to find the Cadence library archive. So we're gonna have to find the Cadence library archive where the slow.lib is present. So you can find it from anywhere because I've used a dedicated path. So you can do it from your RTL subfolder, or you can just go back one step into your full header. You can go back another step as well. So now you are in your home directory, in your home user 41 because I use the 41th ID for creating the lab manual. Now I'm using user 11. So according to your user, you're gonna have to change it. So let me just copy this and paste this. So you're gonna have to edit some things like your user. So it will be user 11 for my case. Then you're gonna have to give a space here and .tar file. So basically we're trying to find something within our home user 11 tag. So you see this is your folders within your user 11 home, and this is your tag folder. Within this tag folder there is supposed to be a .tar dot z file, and we're gonna try to find it. So why are we trying to find this file? This star.gz basically contains a lot of libraries within it. And since all the libraries take up a lot of space, usually in your Cadence or in your Linux interface, it's gonna be compressed into a zip folder. So this is like a zip folder for your Linux. So why Cadence distributes libraries this way? Technology libraries contain many files, timing models, documentation, multiple PVT corners, and so on. So a single archive simplifies the distribution. The compression significantly reduces the file size for transfer and storage, as I mentioned earlier. So if I just press enter now, it should be able to find the tar file. So it has find the tar file. Actually, there are multiple tar files, your GP, DK tar files, and all of that. All of these are present inside your tag. So this uh, 45 nanometer tar file and all the other tar files, which are inside the tag have been identified. So don't get confused whether we're inside this or this tag file. We're actually inside this tag file. We're trying to find the tar file within this one. And inside this, there are one, two, three, four tar files, four compressed folders. One of them is this one. I think someone else removed it and brought it out. And there are three other tar files, and the one that we're gonna work with is this one, Genus GUI tar.gz. So what are we gonna do to extract this tar file? So we can go inside the cake and see for ourselves. tick, ls. So it has these tar files like this one, this one, this one, and this one, these four tar files. So now we're gonna extract the tar file so that we can use this Genus GUI RK file. So for extraction, we're gonna use this command, just copy it and paste it, space here, and space here, and everything seems perfect. So we're basically using the tar xpzf command. Your xpzf stands for, X stands for extracting, V for verbose, Z for unzipping, and F is the file name. This basically will extract the tar.gz file, and this part of the command basically means after extracting the file, we're gonna put it inside your text folder. So we are inside the text folder right now, but let's say we were inside our RTL, then if we had just used this part of the command, then the extracted file would have been within your RTL folder. But here, if we just use this whole command, no matter whether we are inside your RTL or any other file, it's gonna be extracted in your text folder, which is our desired location for our tar file. So I'll just press enter. Then everything has been extracted and it is still getting extracted. So yes, so everything has been extracted that is within the Genus GUI RK file. So if I just press ls again, you'll see that there was a Genus GUI RK.tr.gz, which was the compressed tar file, and this is our extracted file. So let me clear it up. So we have extracted our tar file. It is within our text. Now we have got to copy our desired library into the .lib. So we're gonna have to at first find our library, our .lib files. So find home user .lib, Control C, Control V. So give a space here. So what we're doing here, inside the Genus GUI RK file, we're trying to find all the libraries available. As I mentioned previously, there are multiple libraries, and we're gonna try to find all of them, and from those, we're gonna select our desired one. So enter. You're saying something like permission. Okay, my bad. We are using the ID 11 instead of 41. So yeah, these are the libraries present within your Genus CUI RK folder, typical.lib, there is slow.lib, there is fast.lib, so fastmod.lib and all of that. So these are all the libraries that are inside your Genus. As I mentioned earlier, for emulating the worst case scenario, we're gonna use the slow.lib. So we're gonna have to use this slow.lib library. So what we're gonna do is we have created a project directory earlier, right? This is our project directory. And as I mentioned earlier, RTL constraint was for your RTL and SGC file. Synthesis was for your Genus. Output was for your netlist and reports. And this list subfolder was basically for your library. We're gonna copy and paste our slow.lib in this libs subfolder of our RTL synthesis directory. So the command that we're gonna use is this one. Control C, Control V. So what we're doing here, we're copying the path home user 41 take. It should be user 11. Let me fix that. Slow.lib. Basically, this directory, we're copying this path to our full header underscore lab libs subfolder. So let me fix this. This will be 11. We're copying this path and putting it within our libs subfolder. So just press enter. Then seems to be some sort of mistake. Mm, okay, the problem was this change directory command. It shouldn't be here. It will just be copying this path to this folder. So basically, what we're gonna have to do is remove this. Mm, and I think it should work right now. User 11, okay. Press enter. So the path has been copied. We can see for ourselves. We're gonna enter our um, let's get out of click first, then enter cd full header lab tree inside our lab tree, then cd libs lives, so ls. So you see inside your libs subfolder we have our slow.lib, which is our desired location for our library that we're gonna use. So the slow corner represents worst timing, as I mentioned earlier, which gives the most pessimistic and therefore safest delay estimates and all of that. So we're gonna start with creating the SDC file, our constraint file. So we're gonna have to first navigate to the constraint directory and create the SDC file. So go back one level cd and we're gonna enter our uh, SDC, our folder constraints, where we're gonna keep our SDC, our synopsis design constraint file. Again. So within our constraints file, if I check, there is nothing. So we can create our SDC file. So just you could have just used this command in order to directly go from anywhere to your constraint file. Same thing, we did it step by step. You can do it in one step. Now we're gonna create the full header dot SDC. So nano full header dot SDC. Press enter. Then you're gonna have to copy and paste this one. Control C and paste full header timing constraints. Set max delay 10. From all inputs to all outputs. So it's basically saying that the delay from any input to any output will be 10 units or 10 nanoseconds as we mentioned earlier previously. And since this is a combinational circuit, there is no scope for any clock or any time period or anything. We don't need to specify any of that. We're gonna just specify our maximum delay that our circuit will allow. So after that, press Control O, file name to write, fulada.sdc, OK, enter, then Control X. So the file has been created. Check whether it has been created or not. Yes, we have created our fulada.sdc file. So we have created our RTL synthesis environment Now we're just gonna have to run the Cadence Genus, and we're gonna do it at first manually, and then we're gonna automate the flow using the TCL script. One thing to remember is the file has been extracted once, so the next time you're gonna or I'm gonna run the Cadence Genus, I don't need to extract it again. I can just directly go to this step, okay? Or maybe if I have everything, I don't even need to go through all of that. I can just run the Cadence Genus. So if I want to create another project directory for, let's say, RTL synthesis of counter, a 4-bit up counter, for that, we're gonna have to create all of this directory for the counter as well. We're gonna have to go through all of these steps. You're gonna have to write a different RTL code and a different SDC code. But the only steps that we're gonna have to skip is this, find the tar file and extracting the tar file because I've already done it in my user 11. So we can now start with running the Cadence Genus manually. So the first thing that we're gonna have to do is load the Cadence environment. So for that, start session, wait for a bit. I think we have got back our connection. Mm, wait, what can we use? Okay, we got locked out. We have logged in again. So start with our C shell. CSH. Okay, then we're gonna have to source our set of files. CSHRC. Okay, now since we have loaded our Cadence environment, we can start with our genus. So we're just gonna have to write genus and wait for a bit. Let Cadence load the genus tool, and it will take some time. Just have patience. It's loading the tool scripts. So our Cadence Genus has loaded. So when you will see something like Genus root 1, you understand that your Genus has started. So your Genus has started. We can start with our RTL synthesis. At first, we're gonna have to go to our synthesis folder. You see our directory. This synthesis folder is a folder where we're gonna do our synthesis, and that's why we're gonna go to that specific folder. Right now we're in constraints, if I'm not wrong. Yes, we were in the constraint folder. Now we're gonna switch to our synthesis folder. So just copy and paste this command. Control C. Everything seems alright except the user ID. Change it to whatever user ID you're using. So press enter. We're inside synthesis. The reason we're doing this is because Genus working directory should be synthesis since all the relative paths in the TCL script created later on will be with respect to this location. So we're under the synthesis folder, so we can run the synthesis commands manually now. Let's start with setting the search path for our library. What is our library? Slow.lib. Where is it present? It is in our libs. It's here in this folder or subfolder. So we're gonna search for that. So we're gonna search for the path to that folder and set the path so that my Genus knows where it has to find the library. So let's set the search for everything seems okay. Enter. So setting attribute of root slash and so it's working. So we're gonna have to set the search path Genus uses to locate our Verilog or RTL code. So for that we're gonna have to copy this one, Control C and paste. See, I think it's all right. Okay, it's all right. Now we're gonna have to load our slow.lib. For that we're gonna have to use the read libs command. Control C. Okay, message summary for library slow.lib, invalid value or missing a function. There might be some warnings, so you can just ignore all of them. No need to be bothered about it. Now we're gonna have to read the full header.b, our RTL code. I think it has read my RTL code. Now we're gonna build the internal design hierarchy for our full header. For that, as I mentioned in my previous video, that if we use the elaborate, it's gonna create an internal design hierarchy. That hierarchy will instantiate the modules. It will evaluate the constants, the generate statements, and all of that. And basically, it will tell my genus the internal structure of my code. So my code will now know what it has to synthesize. It will have a proper idea of what my RTL code is intending to do. So just copy it, paste, elaborate full header, enter. So the elaborate, I hope it has worked perfectly. I think it has worked perfectly. No issue. After elaboration, we're gonna have to read the constraint. Based on this constraint, we're gonna do our synthesis, right? So we have to read the SDC file, Control C, Control V. So read the SDC file. This constraints full header is just specifying the path to my SDC. Enter. All successful. Failed 000. So now we can start with our synthesis. The first part of our synthesis was elaboration. The synthesis mainly composes of four parts. The first part is basically elaboration, and the next three are your generic synthesis, your technology mapping, and your optimization. But for that, we're gonna have to set a level of effort that Genus will use. So we're gonna use medium effort. We have low effort, high effort for each of the synthesis stages, but we're gonna go with the medium one, the middle ground. So let's start with our generic effort. Control C. Mm, Sorry about this. Okay, so start with our effort part, generic synthesis. Command not found word for it. So I got locked out. That's why I had to load Genus and redo all of these steps again. So we are back here at this command. So I have fixed the level of effort for my SynGen. Now I'm gonna do it for my synthesis mapping as well. The same thing for my synthesis optimization. Okay, I've set the effort level for my synthesis steps. So let's get right down to business. So first we're gonna do generic synthesis. It is a technology independent optimization, converts my RTL code into abstract, generic, and or XOR gates. It will not use any library cell right now, just your generic gates. So in generic, okay, everything seems to be working. Now we're gonna do syn map, which is our technology mapping. Now the generic gates will be replaced by my standard cells from the slow.lib. And finally, after mapping, we're gonna do post map optimization. Here we're gonna insert some buffers, gate resizing and restructuring and all that for optimization, reducing the power area, making sure that the timing requirements are met and all that. So everything has happened that needed to happen, and we have done our RTL synthesis. So what we can do here is we can do report mapping, reporting, and we can write the full header netlist. So we can do either first. Let's start with the report. So report area. So it will give you the area report of your full header. We'll discuss this later on. Let's just go through all the steps. Report timing. Okay. Then there's report power. There is report gates. Okay. And after that, Control C, we can write our HTL code into our header netlist. And the exit also got written at the same time. So I think both commands got executed. We have written our full header netlist as well as we have exited our Genus terminal. So we're basically gonna see something like this. This will be our new project directory. So cd, where are we right now? If we're at pwd, it will show us the directory. We're in user 11 home. So let's enter text. What do we have inside text? We have all of this. And okay, let's get out and let's enter our ladder on F3 OS. We have 1, 2, 3, 4, 5 subfolders. Initially, those folders were empty. Then we wrote our RTL code. We wrote our constraint SDC file, and we set the path for our store.lib within our libs, and we did the synthesis in the synthesis folder, and we should get our outputs here, the output folder. So if we just write free, it should show us something like this. So yeah, we have our constraint, our full header.sdc libs slow.lib output, my full header netlist. We have just written our output, right? We have written our output full header netlist. We didn't write any report. We just wrote our full header netlist. That's why in the output folder we just have our full header netlist, not the reports. We can write them later on. If you want, you can write them right now. But I will show it while automating the flow using the TCL script. So our synthesis has your all the synthesis folders. You don't really need to bother about all this. So this was all for synthesis. We got the same except for the .rpt, which we will see while writing our TCL script. But for now, as far as manual is concerned, this was all that I wanted to show. So we can do the same thing. We can do the same thing using a automated script. Automated script, this one. So I'll show it right now. Okay, let's start with automating the RTL synthesis flow using a TCL script. So typing each command manually is useful for learning, but tedious at the same time. So in this section, what we're gonna see is we're gonna do the entire flow that we saw in our section 5 using a single command, which is a TCL tool command script, tool command language script, and we're gonna do it after navigating to the synthesis directory and creating the TCL script. So we're gonna have to go to the TCL folder. Sorry, the synthesis folder. We're gonna write our TCL command or TCL script in this folder, and then we're gonna run our cadence. So let's get started. So wherever you are, if you just write this one, it will automatically take you to the synthesis folder. So we're inside synthesis. We're gonna write a TCL script. I'm gonna name it FF ladder Genus script. You can name it anything else. Control C. Okay. So we'll get this window. Now we're gonna have to copy and paste this. I have already copied it. Control A, Control C. Just right click and it will be pasted. Everything seems alright. So Control O, Enter, Control X. So you have written your TCL script, your tool command language script. So one thing that you should know is after running it manually, as you can see, I have exited the genus and then re-entered. And after that, I am actually gonna execute the TCL script. I haven't re-entered genus yet, but I'm gonna do so. So let's start genus. Wait for some time. Wait for the genus tools to load. So I said so because if we hadn't exited genus earlier after manually doing everything, it could have created some sort of conflict. But right now, since we have already exited and re-entering genus, so I don't think there will be any problem. So we can just start the genus and run the script while being in the synthesis directory. Where are we? We were in the synthesis directory. Let's just check. Yes, we're inside synthesis. So we're gonna just source the TCL script, Control C. So all the steps that we did earlier, elaboration, generic synthesis, technology mapping, and all of that has been done. So all the commands here have been run. We have set the path. We have read the libraries, the RTL code. We have elaborated our full adder. We have read our SDC for the constraints. We have set the level of effort. We have done synthesis of generic synthesis, technology mapping, and optimization. We have reported area, gauge timing, power, and all of that. And we have also written down our area report, gauge report, timing report, power report, and overall design report in our output directory. And we have also written our full adder netlist in our output directory. If you remember, we already had a full adder dot underscore netlist. So if we run something again, if we do the RTL synthesis again, it will just override the previous full adder netlist. So we can check it again. Just write, just go one step before. So we are inside our full adder lab tree. So we have these five subfolders. So if I just write three, it should show us all the files. So our constraint, our libs, our output. In this case, we have the reports as well as our full adder netlist. We have our RTL, we have our synthesis files and our TCL script, and we have some genus.cmd log txt. These are not important for your lab, but I have added some sort of purpose for all of this extra files that are generated. You can read it at your free time. So that was all for your automation of RTL synthesis. So what we can do now, we can launch the graphical user interface. So the command in line flow, what we did earlier to run the synthesis, it gives us an intuition, but we cannot actually visualize what we are actually synthesizing to, right? We're synthesizing to a macro cell of a full adder, right? So if you want to see that, what we can do is we can use this command GUI show graphical user interface show. We just press enter. You will see something like this. So here you can go to file. I think it will take some time to load and all. Let's give it some time. So everything has loaded. So we can see the design hierarchy. We have our standard cell. We have our net list. We have our terms, our input and output terms. A, B, C in input, SAM and C outer output. These are the net lists. We have 5 networks or net lists. And we have one standard cell, the add fx11. If you want to see the schematic of this full adder, so just press here, go to schematic. You will see this one. You can bring it over here. So this is your full adder schematic after RTL synthesis. As I mentioned earlier, there will be just one or just a single standard cell that it chose from the slow.lib library. These are your inputs, these are your outputs. So you can see the reports from here as well. You can see, let's say, the gate count and all of that from here. The power report, everything here. If you want to see all of those things here, or we can close it. We can see it here. We have our reports in the output. So if we just navigate to our output, uh, where are we right now? PWT. We're inside full adder. Okay, then CD output. We should be inside full adder. So now I think we need to use GUI hide. If we use GUI hide, come back, it's the same. Okay, let's try to do it. Let's try to see which report, area report. So I'm just gonna invoke source. Let's use cat. I don't know if it will work or not. Let's try cat area dot it's showing one. It shouldn't show one. I think in order to visualize these reports, let me try this one. Cat see. So showing the same thing. We're gonna have to at first exit Genus. Okay, we're inside synthesis. Another CD output. So we're inside output. We are no longer inside our genus. We're inside our normal VLSI user. So get area dot EP. So now we can see our area report. So this is your area report full header count 1 cell area 5.13. Okay, you can see the net list as well. Cat. This is your net list. You can try to see the other reports as well. So I think we have covered everything that could be covered. We have at first done it, we have at first created the directory, then done the Cadence Genus synthesis manually. Then we did it automatically using a TCL script. And lastly, we saw the graphical user interface. We saw the schematic view. So I think that's all that is required for this lab. So I haven't discussed about the reports yet. I will do it in the next video. But as far as the RTL genus synthesis is concerned, this is how you can use the genus tool of your cadence in order to synthesize your RTL design. So thank you for listening to me. Jazakallahu khair. Assalamu alaikum warahmatullah.